In tectonically active areas like Tokyo, where the Tokyo Skytree towers over the city that's prone to major earthquakes, it's crucial that buildings are designed to cope with the movement and the stress created by these seismic events. Designing aseismic buildings is an important part of architecture across the world. Here in San Francisco, where the San Andreas Fault is building stress threatening a major earthquake in the near future, major buildings like the Transamerica Pyramid here must be designed to cope with the earthquakes that are expected in this area. There are several features that can be used or can be added to a building to increase its resistance to earthquakes shaking. One of the simpler of these is X-bracing. Bracing the vertical strengthening beams within a building with these distinctive X-shaped braces. Let's see how that works. This is my earthquake simulator. We're going to have a look at how different types of structures will resist an earthquake and what design features could be added to a building to reduce the chance of damage. So we have my earthquake shake table here ready to move, and to simulate the buildings I have some wooden blocks. Let's start with the simplest structure of all. This is an unreinforced masonry structure, typical of the houses we might find in Britain, where you have stone or bricks just sitting on top of each other, held in place by mortar, with no reinforcing at all. Now, if we shake a building like this, it will fail. It'll fall down. Okay, if an unreinforced masonry structure will fall down, what could we do to perhaps reinforce that? How could we make that more stable in an earthquake? What we could do is start to brace the building to resist that shaking. So we could put some bracing rods. I've got some pieces of wood here that I'm going to fix with some tack to form what's called an X-brace. So I've fastened the two upright structures to each other. Let's see how they resist an earthquake. We have an unreinforced masonry structure here to compare. We can see that with the same amount of shaking, the unreinforced masonry structure collapses. The one with the X-bracing, though damaged, has stayed standing. Another way of bracing a building is by employing K-braces. These connect the vertical beams to the horizontal. Let's see how these work. Okay, so we've seen how one type of bracing could help prevent damage in an earthquake. But there are other ways of bracing a structure to resist the effects of an earthquake. This time, we're going to connect the upright structures with the horizontal ones. This makes a type of bracing we call K-bracing. And again, let's have an unreinforced masonry structure to compare it to. So, if we have an earthquake, again we can see the braced building stays standing, the unreinforced building collapses. Let's compare that with both types of bracing. So we know both of these types of bracing are better than no bracing at all. Which one, though, is more effective? Let's see. So we can see with the same amount of shaking, although it took longer for the X-brace to fail than it did for an unreinforced masonry structure, we have one building that's failed, the other, again damaged, but still standing. A more high-tech solution, certainly in tall buildings, might be to use a counterweight, computer-controlled to resist movement. See how the weight moves in the opposite direction to the shaking. Tall buildings create a particular challenge for engineers. Trying to make a tall building earthquake-proof is difficult. One of the ways that's been done to make a tall building earthquake-proof is to put a counterweight at the top of the tall building that moves in the opposite direction to the way the building shakes to keep the building upright. Now for this, for a counterweight, I've got some steel ball bearings in a plastic cup that I'm going to put on top of the building to act as my counterweight. And as a comparison, I have another tall building without any counterweight. Let's see what happens when an earthquake strikes. We can see that the building without the counterweight has failed. The building with the counterweight stood up far better to the shaking of the earthquake. Base isolators provide another means of making a building resist earthquakes. In this case, though, they separate the building from the shaking ground. See how this works. The final type of earthquake-proof design that we're going to look at are base isolators. Now for this, I'm going to use some small pieces of round dowel and a piece of wood to build my building. Again, as a comparison, let's have an unreinforced structure. And let's see what happens now when an earthquake strikes. We can see with the base isolator, the building stays relatively still while the ground moves underneath it. All the movement is taken up by the isolators. The unreinforced structure, though, collapsed fairly early on. Let's compare this to bracing. So we have our base isolated structure. We'll put some K braces. On here. And let's see what happens when an earthquake strikes. A brace building clearly isn't as strong as one where there's base isolators. But with all of these things, engineers always have to consider the cost as well as the risk. Which of these methods do you think is the most effective? And which one of these do you think is the most cost effective? So, having seen these different techniques, which do you think are the most effective? Which do you think would provide the most protection? Which do you think would be most cost effective for a building you're creating?